This next page is mostly just introducing some stuff that you likely know about and reminding you of a few notational things. So, the notation that I'm interested in showing you is listed here. And mainly, I just want you to know that when you see things that look like the left-hand column in the homework, it means what's in this middle column. So in other words, when you see something that looks like f plus g of x, that means just add the two things together, add the two functions together. And when you see f minus g of x, that means you just subtract the two functions. And when you see f and g multiplied together of x, that means you multiply the two functions. And then this one means you divide the two functions. Okay, so you'll see that notation in the homework. I usually like using this notation on the right to make it a little more clear, but in the homework you might see some of the ones that are on the left there. Be aware of that. The other thing that this box is telling us is, let's say that f and g have domains a and b. So let's say a goes with f and b goes with g. Then when we add, subtract, multiply, or divide two functions, the new domain is the intersection between the two. So that upside down U means intersection, right? It's kind of like, I always was taught, it looks like an N, which is like intersection. That's the best I got. And it's like the opposite of union. So when we write a capital U between intervals, that means you include both the things, right? So when we write down like 1, 2 union with 3, 4, that means you include everything in both of them, right? And so when you flip it upside down, it's the opposite. It means you take what's common to both of them. And so what this, and let me write that down. So this means that we take what the two domains have in common. Now, I usually don't like spending too much time on this page because I think the intention between this section is that you can find the domain for f, find the domain for g, and then look at the intersection to find what their common domain is. The better way to do that is just to subtract the two, or whatever whichever one of these operations you're doing, just do that and then look at the problem and write down the domain. To me, that's an easier thing to do, and so that's what we'll focus on. Let me add the caveat here, which is that when you divide functions, you get this, but there's this added condition. What is this added condition for? It says you take the intersection, but you need to make sure that g is not 0. Yeah, is that what you're thinking, Andrew? Say it too. Yeah, right, exactly. We don't want to, so I'm just going to star this. This is just so that we don't divide by 0. Okay, yeah.
So whenever we write the domain for two functions being divided, we're always going to leave 0 out of it?
Not leave 0 out of it. We're going to leave any x values that make the bottom 0, which is something we've already been doing. Okay, so we'll see one of those on one of the examples, and then let me know if that's not clear. Again, I don't want to spend too much time in it. I really just want to remind you of the notation more than anything. And so down here we've got two functions, f and g, and this notation, f minus g of x, means subtract the two functions. Right, and so we would take the f function and subtract from it the g function. So that's all that notation means. Don't get confused by it. Again, I'll use this notation more than the other one, but in the homework you might see the other one. Devin?
It might be like some kind of printing thing. What is the E on the instruction?
Ah, yeah, this thing?
Yeah.
This means in. It's a Greek letter epsilon. That means that it's math shorthand for n. So this means all x in the set A intersect B, provided that the function is not 0. I know, like, don't worry too much about that. All right. This math shorthand becomes very, very, very helpful when you're in more advanced classes because no one wants to write out what I just said, but you can write it like that, right? It's almost like another language. I mean, it is another language, right? But anyway, it's the Greek letter epsilon. Yeah. Don't worry about that part. Other questions? Okay, and so then when we do the subtraction, I just want to point out that this minus sign distributes. Don't forget that. I'm seeing some people still forgetting that. And so that's going to make it a plus x squared and a plus 2x, right? And so we'll get 2x cubed minus 4x squared plus 6 plus x squared plus 2x. And then we can just combine like terms. We got a couple x squareds in there. So I'm going to add them together. What's the domain of this thing? That's what we want to write down right here. Have you guys figured out domain's important? I've said the word domain way too many times today. It's really getting old, but it's important, right? We're going to think about domain a lot. So if you're struggling with that, please come get some help. What do you think, Adrian? Yeah, I think it's every number, right? There's no fractions. There's no fractions in this, so we're not going to divide by 0. There's no roots. We're not going to divide, so we're not going to take the square root of a negative. And moreover, it's a polynomial, and we already wrote down that polynomials, you can plug anything in there. So the domain of this is everything, minus infinity to infinity. That's a nice one. All right, what about this notation? So this notation means we multiply the two functions. So when f and g are in the same parenthesis, that means you multiply. And so we would just multiply the two things. And we'd FOIL that all out, right? We could FOIL this now. And we'd get the following if we did that. I'm going to jump to the chase, just cut to the chase, I mean. It would simplify down into another nice polynomial. Yeah?
Would it be negative 2x?
Yes, it is. Thank you. Wondering if I messed anything up in there now. 4x to the 4th. But it's going to cancel with this 4x to the 4th.
Oh.
Yeah. I was just thinking that. I was like, where's my x to the 4th? I think that's probably right, though. And this is another polynomial, and so the domain is everything. Woo! We can plug anything into polynomials. All right. All right. This last one is the one that actually we have to think about a little bit. So this notation means divide the two, right? And so when we divide f and g, we will get this. Okay? All right. And now I want to know what the domain is. And so maybe I'm going to pick on Carlos here since he asked a question that was very similar to this one at the beginning. Let's see if he was paying attention. So what do we want to worry about first of all?
Divided by 0.
Dividing by 0. And so what's a good thing to do when we have a denominator that looks something like that?
Factor it.
Factor it, yeah. So let's factor the denominator because that's going to help us see what the zeros are. So I'm going to factor out an x and get minus x minus 2. So I factored. And we want to avoid dividing by 0. And I know I said this before and we'll say it again, but if we want x times minus x minus 2, we want to see when that's 0, we set the individual factors equal to 0. So we take the x and we set that equal to 0, and that's one of them. And then we take the minus x minus 2, and we want to see when that's 0. And so we can solve that, and that means that x equals minus 2. And so we want to write down every number, but not 0 and not minus 2. And so the domain then is from minus infinity to minus 2, minus 2 to 0, 0 to infinity. I'm going to start the next page, just so you know. I use all the class period. I'm sorry, guys, but we've got a lot of stuff to do. Are there any questions about that? And so the main thing I was pointing out here is the intersection of of these two functions. The domain of these two functions are both minus infinity to infinity, right? And this one was also that one because we took the intersection and it was the same. And same thing with this one. And this one is also minus infinity to infinity, except at the points that make the denominator 0, those 2 points. And so we skipped over those 2 points, but otherwise everything else we can plug in. Questions? Okay, I do want to start the next page just because I want to plant the seed. This is kind of an important page too. I know I feel like I probably say that too much, but it's all important. But this is something that I know that people sometimes get tripped up on, and it's very important for calculus and beyond and everything else. So let's just remind ourselves about evaluating functions. And it's going to sound, you're going to be like, oh my gosh, I can't believe he's telling me this. But it's going to get more complicated. And so let's focus in on the easy stuff first. So here's my function, right? 3x squared minus 4x plus 1. And in all these examples, all the f's, f of a, f of 3, all these f's are referring to that f. Okay, so that's my f on this page. What does f of 3 mean? Someone tell me what f of 3 means in words. When you see something that looks like this, what is it telling you to do in words? Nick? Plug 3 and 4? The x, right? So it means replace all the x's, and not just one of them, but all of them, right? It means replace all the x's with a 3. And I know you know that, and we've already done that, but again, we need to start with the basics, and this is an important part of that basics, the instructions, because when we do f of minus a, it's going to have the same instructions. Okay, so when we say f of 3, it means, I'll put it in quotes, the instructions there are like replace all the x's with a 3. Right? And it becomes somewhat straightforward. We just take out the 3 and we put in an x. And I'm not even going to simplify that. I'm just going to leave it like that. Like, yeah, we could simplify that down to a number, but that's not what I'm trying to focus on right now. I'm just trying to focus on the instruction of what that means. When the notation, really. When you see f parentheses and then something's in the parentheses, it means remove the variable and put in whatever's in the parentheses. And so we can do that with not numbers too, like f of minus a, for example. So f of minus a has the same instructions. It's just replace all the x's with minus a. The same way that we just did the last one, except it's not a number. Right? So f of minus a is just going to be 3 times minus a squared minus 4 times minus a plus 1. Okay, I just took the x out that put the a in. The minus a, excuse me. Is that okay? And we can work with it too, right? Like, so we can square the minus a. If we squared the minus a, it becomes positive a squared. We can multiply the minus 4 and the minus a. That becomes a positive 4a. And that's all we can do, right? So we can't do anything else, but that's true. And we followed the instruction and we plugged in a minus a. My point here, and what we'll pick up with next time, is we can plug anything into functions. Even, that was supposed to be a star. Even a star. Let me try that one more time. We can plug a star in too. It's a little bit better. Not much better. It's the same instructions. Take out the x, put in a star. And we can do it with anything. We'll do it with some other weird stuff too, right? We'll do it with a plus h. We can plug sums in. We can plug other functions into functions. So that's what we're moving into next, and that's what we'll pick up with on Friday. All right, thank you. Have a great day. And what we had talked about, we'd started with a couple of basic examples to kind of get our heads around the notation of things before we move on to something more complicated like part C here. Right? And so we're talking about this function, 3x squared plus minus 4x plus 1. And we just started off with the real basic evaluating a function, right? When you see a number inside of a parentheses next to that f, so f of 3, we say we take out all the x's and we replace them with a 3. Right? And I know you know how to do that, and the point of this stuff is not to even simplify this, so I'm not even going to simplify that down. I just want you to see that that's what happened. We took out the x and we put in a 3, right? And we're using that same intuition when we do something more complicated like f of minus a. So even though it's not a number now, it's a variable, it still means take out the x's and put in whatever's inside the parenthesis. And so in this case, it's a minus a. And so we do the same thing. And so notice that the similarities between this equation that now has a 3 in it and this equation that now has the minus a. And we kind of finished off by saying we can plug anything into equations, right? We can even plug something weird like a star in. And f of star would look like this then. Again, we're just taking this equation and we're removing the x and we're putting a star in. And so before we kind of do this more complicated expression, we can even plug in functions themselves. For example, we could do something like, let's do two silly things like f of star plus, I don't know, this squiggly thing, the circle thing. If we want to do f plus squiggly thing, star plus squiggly, we just take out the x and we put in the star plus squiggly. Just made up that squiggly on the spot. You like that? Adrian loved it. But anyway, it's the same process, right? We just take out the variable and we put in whatever is inside the parenthesis. And yes, that's nonsensical, right? That doesn't have a real meaning. But oftentimes we want to evaluate functions with other functions that do have a meaning. Kind of like this next example. But I want to just pause and see if that's okay. Are there questions about this concept at all before we look at one that looks like this? So this is a pretty important expression, all right, and I always like to harp on this. I usually like to put this on tests and things too, because this is an expression, if you take calculus, you'll see this expression again. You will see this in a calculus class. It's the definition of a derivative with some added things to it. But anyway, you want to get good at handling an expression that looks like this. And so if we want to handle something like this, I'm just going to go ahead and write out the fraction part first. It's going to be a fraction, and the h is in the denominator, right? And let's think about what f of a plus h looks like. It's going to look a lot like this f of star plus squiggly. Right? We're going to take out the x and put in an a plus h. And so that's going to look like this. Right? We'll have 3 times a plus h squared minus 4 times a plus h plus 1. Oh, I messed that up on the last one. Anyone else notice that? I wrote minus 4 for some reason. I think I was just copying this down. This should just be a plus 1 from that previous thing. You want to see that? Sorry about that. Let me just tell you up front, I'm having a rough day in terms of writing the correct thing down. I've been writing the wrong thing down all day long in my classes. So I hope someone's awake and is going to keep me honest today. But anyway, this is what a plus f of a plus a would look like. So this expression here is f of a plus h. And then if we subtract f of a from that, it would look like the function with an a in it instead of an x, right? And so that would be 3a squared minus 4a plus 1. And so this is now my f of a. And you can see I'm being careful about this, right? I've got my f of a inside its own brackets because we're subtracting the whole thing, right? We're subtracting the entire function. And so we want to make sure we're careful about distributing that negative sign. That negative sign is going to distribute through that parenthesis and switch all the signs around, right? This is one step that people often get tripped up on. It's a very small thing, but be careful about that. Yeah?
Is it really a big deal whether or not you have brackets or parentheses on the
No, yeah. I just used brackets because I had already used parentheses, and sometimes when you do lots and lots of parentheses, it gets hard to keep track of. But yeah, if you want to put parentheses around the outside of that, that's fine. Are there other questions about this so far? Because now we just want to kind of simplify, and it's some algebra, and it's stuff that we kind of reviewed previously. And usually the tough part of these type of problems are just writing this step down. Writing down what f of a plus h minus f of a over h looks like. And so this first expression is my f of a plus h, and the second one is my f of a. Folks see that? You want to should I clarify it at all? Is there any part of that that's confusing? Let me just note, too, one thing that often people wonder is, this squared is still the same squared that was in the original function, right? So this original function had a squared, and so when you remove the x and you put something else in there, it still has the squared. We're not removing the squared part, we're just removing the x. So that's one thing I want to point out. And then when we go ahead and we do this, when we square out a plus h, we do a plus h squared. Be real careful with that, right? That's one of the common pitfalls. We need to think of it as a plus h multiplied by itself, and then make sure that we FOIL. Right? Don't just square those two terms. So we feel okay about this? We're all right to continue? Yeah.
I just want to make sure,
Yep.
Because it's minus the f of a, so that all has to be done first, and the solution to that is subtracted.
Yeah, that's right. So the other way to say that is, before we combine anything over here, we need to distribute the minus sign. Yeah. So that's what I'm going to do in the next step. I'm going to square out the a plus h, and I'm going to distribute this 4. So I'll send this 4 through the parentheses, and then I'm going to send the minus sign through those parentheses there. And we at this point, we're just simplifying and seeing what we can simplify things down into. So it would look like this, right? When we do a plus h squared, we get a squared plus 2ah plus h squared. And then when we distribute that minus 4, we get a minus 4a minus 4h. And then we still have the plus 1. I'm just going to leave this in a bracket for right now. And then I'm going to distribute that minus sign like we said, right? So this switches all the signs around. So minus 3a squared plus 4a minus 1. We still have it all over h. And so since Rachel asked that question before, we're almost ready to contribute or to combine multiple like terms here. But what do we need to do first? Kind of similar to what you said. There's one thing that's stopping us from combining like terms at this point. Jason?
Distribute the 3.
Yeah, we got to get this 3 through there first, right? If we distribute this, then we'll have a whole bunch of terms that are all on the same line, and we'll just be able to to combine them, right? And so the next step is to distribute that 3. We'll end up with the 3a squared plus 6ah plus 3h squared. And then everything else just carries over. And so the way these problems work, and the way they work in calculus especially, is lots of things end up canceling out, and we usually end up with something that's not a fraction anymore. And so, for example, you can see that we have like a plus a squared and a minus a squared, and so those two things will go away. Right? We've got a minus a and a plus 4a. And then we've got a plus 1 and a minus 1. So a lot of the stuff on the numerator just cancels out. And what we get left with is a whole bunch of stuff that has a common factor. And so what's left is 6ah plus 3h squared minus 4h over h. And so there's a lot of variables flying around here, right? We've got a's and h, but that's okay. We can just treat them like variables, and we can factor something out if they have something in common, right? So what variable do they have in common in the numerator? Yeah, good. They all have an h. So we can pull an h out of the top, and we'll get 6a plus 3h minus 4 divided by h. And we wanted to do that because, like I said, things usually in these problems, they cancel. And so you can see that the h's now cancel. And we're just left with a nice final answer that's much simpler than the original problem looked. 6a plus 3h minus 4. And again, I like to harp on these on tests and things like that, so you might want to take note of this and make sure that you answer these questions in the homework and they make sense, because I like these problems because they have meaning to them, and you'll see this expression again in calculus if you end up taking that. So, yeah.
I just had a quick question
Yep.
on the second line.
Yeah.
So I understand why there's a squared and h squared, but why is there 2ah's?
Yeah, that's a good question. So that's the tricky part that people end up, if you just distribute the squared through, people always just want to take the square and send it through there and multiply it by the a and the h. And you'll get the a squared and the h squared. But when you FOIL, what you end up doing is you end up having this a times that h and this a times that h. And so you get two things that are an a times h. And so that's where that middle term comes from. So if you forget to FOIL, you miss out on that middle term, which is what makes it wrong. Does that make sense? Other questions about this one? Okay, give some of these a try in the homework, and then we can talk about them next week if they're tripping you up a little bit. And so I want you to take this idea to the next page. This is why I did this page right before the next page. This idea of f of a plus h is taking the function a plus h and plugging it into the function f. And so that leads into the next page, because the next page is all about composition functions. And composition functions are just that, one function plugged into another function. Okay, let's take a look at these diagrams. You guys know I love these diagrams. We've got the beans. The beans are back. And the whoopee cushions are also here. The whole gang's here. Okay, let's talk about what a composition function is, or a composite function. Excuse me. So let's look at this notation first. This is the notation. When you see something that looks like f circle g of x, that means this. That means the g function is being plugged into the f function. So I'm going to write that down. This notation means the function g of x is plugged into the x in f of x. Using the same notation and the same sort of logic as we used on the last page. right? It's literally the function g is inside the parentheses of the function f. And so using that same notation, that same logic, it means take out the x and put in the function g. Now before we look at a couple examples of that, practically, so first of all, this is an example of it right here. This square root of x squared plus 1, that's a composite function. And let's think about how that composite function was built. And so it's kind of like we have a function g, and let's call that function g x squared plus 1. And we have another function f, and let's label the function f as the square root function, square root of x. And so this is our original or final composite function is the square root of x squared plus 1. And I'm trying to think about what two functions I would need to plug into each other that would give me that. Because if this is my g and this is my f, and I take the function g and I plug it into f, in other words, I take the function x squared plus 1 and plug it into f, that notation means remove the x and put in x squared plus 1. And so this would be exactly what's written there, square root of x squared plus 1, because I took out this x and I put in this entire function into that x. And just like we did in the last page with f of a plus h, very similar to that. Jason?
Like I used to always like tell myself, remember with this sort of thing, it's just like think of it as f of g of x, like f of g of x.
Yeah, that's a good point. And so that actually brings me to my next point. So Jason's point is, when you say f of g of x, you're listing them from the outside in, but then when you actually plug a number into that function, the number comes from the domain of g. And so that's what our bean diagram is showing us here. So the bean on the left here is the domain of g, and then the bean on the right is the range of f. And so you can see that things that we plug into this function come from the domain of g, and they get sent to, because they eventually get plugged into f, they get sent to the range of f. And so that's what this diagram is showing us. It's kind of like we take our input and we plug it into the function g, and that's what this middle is. So this middle bean is the range of g. And then things that come out of the range of g get plugged into f, and they go into the range of f. And so you can do it in two steps like that. You plug them in one at a time. Or if we have the composite function already made, and it's already one function inside of another one, then we have this function, right? We have f of g of x, and that takes x values in the domain of g and sends them directly to the range of f. And that's what's also being shown. This is a specific example in this, our whoopee cushion here. When we take an input, it comes and it goes into the g function first. That gets evaluated in x squared plus 1. And then whatever x squared plus 1 equals, it gets put into the function f, and we take the square root of it. And that's literally what's happening, right? We took that, and then we took the square root of it, because it went into the function f. And I know this can be confusing, and I honestly believe that a lot of the confusion that arises from this particular topic is because of the notation. The notation looks weird, and we're talking about domain and ranges, which can also be a little confusing. But in practice, all we're doing is we're following that same intuition about plugging things into other functions. Except instead of a number, we're plugging entire functions in now. Can I clarify anything before we look at an example? I think examples can help with this if you're a little confused. So let's look at these problems down here. We're going to have two functions. Okay, we've got a function f. I wrote it right here. It's x cubed plus 2. And we've got my function g, which is the cube root of x. Is this a little bit blurry? Let me see if I can fix this right now. All right, resume video. So I've got two functions. My f of x is x cubed plus 2, and my g of x is the cube root of x. And you can see what we're going to do here. is we're going to plug them into each other. We'll plug G into F, we'll plug F into G, and then we'll plug F into itself, we'll plug G into itself, and then we'll plug some numbers into there too. And so for example, the first one here, remember this notation, F circle G of X means F of G of X. In other words, we take the function G and we're plugging it into the function F. And so that notation just means take out the X in F and put in the function G. And so practically speaking, since G is the cube root, it means this. And if that makes you feel more comfortable, then think of it like that. And so in this case then, this is just the notation here, right? And so F of G of X then equals, we're going to take out this X right here, and we're going to put the function G into that. And so that's going to end up being the cube root of X cubed plus 2. You see how that worked? Yeah, and so the next step is then, can we simplify it? And so we've got a cube root that's being cubed, and so those two things cancel out good. And so it's just X plus 2. I get a lot of questions on these, like, should I always simplify it? And like you'll see in a second, you'll say, oh, should I simplify that more? And simplifying is nice, and it depends on the problem, but generally speaking, on tests and things like that with these problems, I'm not trying to test your algebra skills for the most part. I'm usually trying just to see if you understand the concept. All right, so the point of these problems is not to see if you can do algebra and distribute and things like that. It's to see whether or not you understand what a composite function is. What about the next one? So the next one is G circle F now. And so G circle F means take the function F and plug it into G. Right? So we're doing the opposite. And so we're taking the X cubed plus 2 and we're plugging it into the X in the cube root of X. And so when we do that, we end up with the cube root of X cubed plus 2. Can this be simplified? Got a couple yeses, a couple no's. I will say the answer is no, but why?
It's not multiplication.
Is that what you're thinking, Adrian?
Yeah.
Yeah, the plus sign is what's stopping us from simplifying this more, right? Lots of people want to pull that cubed out. You can't remove that cube because of that plus. That's one of the common mistakes that was written down a couple pages earlier in that box that said common mistakes, I think. It said don't make these mistakes, right? This is one of the things. If you've got addition between those two, you cannot remove the x. If it was multiplied, yes. All right. Questions? Just think about f of f. You can, f of f is a little bit strange because it's like you're taking the function f and you're plugging it into itself. But the notation is the same, and it should be understood as the same, right? And so it means take x cubed plus 2 and plug it into the x in x cubed plus 2. All right, and so this would look like x cubed plus 2 cubed plus 2. And this is the point where someone was like, oh man, now I have to simplify this? Like, no, I'm not asking you to do this multiplication. I don't want you to see that you can cube things out. It's going to be long and tedious, and not the point. The point in these problems is to see your understanding of composition functions. So in other words, if this happened to be a test question, this is a very good answer. What about plugging numbers into this stuff? So let's look at this one, this f of g of 2. And so 2 must be in the domain of g, since we're plugging it into g first. And so this just means take the function f of g and plug a 2 in. Right, and so we have the function f of g right here, right? We just spent some time figuring out what that was. And so we can just use the function that we had, which ended up being x plus 2, and plug a number in there. And so this is going to equal 2 plus 2, which is 4. And 4 must be in the range of f. Right, so 2 is in the domain of g, and 4 is in the range of f. Questions? All right, finish this page. We've got 2 left. So plug a number into g of f. So the second one means we're taking g of f and we're plugging a 3 in. And we have g of f right here. Sorry. And the second one means plug g into itself. All right, take a minute and try that one. And check with someone next to you when you finish. Yeah? I just use the simplified form.
Oh, okay.
You could use this form too if you want. But then we'd have, so let me just write that down. You could say cubed root of 2 cubed plus 2. And then the cubes would cancel. The cubed and the, I just wrote squared, sorry. That's like the 5th time I've done that today. I've said cubed and wrote squared. It's been a rough day. Anyway, those 2 would cancel and you'd still end up with 2 plus 2. And you'd still end up with 4. So either one of those would be okay. Okay, anyway, try these last 2 though, and if you're stuck, I'm happy to help. And if you're stuck, you know, you should check with the person next to you for sure. And we'll reconvene in just a minute. I give anyone a hand?
You know, the square root of the 3 square root of x, right? Yeah, just I don't know before that. That's 3 square root of x and 3 So I understand. Like it's easy. That's where I learned because then you have this like this. Yeah. No, yeah, like it's 3 completely faster. That's all I always just run to the like just multiply it by itself.
G is the first thing, so I didn't square the root, nothing, just like a root of that.
That's what I was trying to
So you don't get
Really hot the other day, and now it's like
It's yeah.
cubes plus 2.
It's super cold. I love it. What would I like in service?
I love it.
I know. I have so many cute outfits. I can't wait. Like, if I have like fall, it's more like intense. Like, my sweaters are gorgeous.
Okay, that's a good point. So you can go further with that. Like, you know, that's the right and
I barely have any summer clothes.
I also have like
I love fall so much.
it's so nice.
Yeah, like I have a big sweater. It's like black and white, and it's like each thread is like one black, one white. I love that color.
I'll write that down.
Yeah, like that. But it's like brighter colors. Like it's like white. It's like gray and black. I mean, you might lose so many times towards the straw. Yeah, that was probably like last week. No, they were on sale. These are on sale.
right now.
All right, so lots of folks are on the right track. Let's look at these 2. So when we plug a 3 into this first one, we can use the function that we just found before, right? We can use this as our g of f, and so I'm going to use that one. And so I'm just going to take out the take out the x and plug in a 3. So we'll get 3 cubed plus 2 inside that cube root. And so that's just going to be the cube root of 29. And we would just want to leave it like that. Is that one okay? about this one? This one's good. A lot of people had questions about this, and you're thinking about it right, so that's really great. So g of g means take the cubed root of x and plug it into the cube root of x. And so that's going to look like the cube root of the cube root of x. And so, yeah, go ahead.
Could you like make that into the 9th root?
Yeah, awesome. That was the next step, and I had a lot of questions. People knew they could do something, right? And this is this is something we talked about. This is in the radical section. If that was got to dust the cobwebs off that section. But maybe if we rewrite it as exponents, it looks a little easier to handle, right? It's actually x to the 1/3 raised to the 1/3. And so now it's an exponents problem, which we are likely, I don't know, I'm better at exponents than I am at radicals, at least. And so now we have an exponent raised to an exponent, and what do you do in that situation? You multiply them, right? And so we get x to the 1/9, or, as Jason said, the 9th root of x. We could say that. Right, so we don't add them, we multiply when we have an exponent raised to an exponent. Any questions about this idea? I feel like you guys got a pretty good grasp on it, which is good. Let's take a look at the next page. Not sure how far we'll get, but let's see. We want to leave a few minutes for the quiz at the end here. Is everyone all set with this page? Don't see anyone writing. So on that page, what we were doing is we were taking two functions and we were putting them together. Right? We were composing them. On this page, it's like we're starting with something that's a composite function, and we're trying to think about how we can pull them apart into two separate functions. In other words, we're kind of thinking of this first one as f of g of x. That's some composite function, and let's try to think of two individual functions that when we plug one into the other one, we get this, x to the square root of x plus 1. So it's doing like the opposite of what we did in the last page. So for example, when I look, and the kind of, dare I say, fun thing about these kind of problems is there's usually more than one answer. There's usually infinitely many answers, quite frankly, and so you get there's some puzzle kind of feel to these. It's like, ooh, I can think of this one, and maybe someone else thinks of a different one, or something like that. Do you have one in mind, Andrew? Or do you have a question?
I have one in mind.
Okay, what do you think?
The square root of x and then x plus 1.
Okay, let me look at that one. So let me write it down. Don't write this down. If we get the square root of x and x plus 1, and then we take f and we take g and plug it in there, this whole thing will be under the square root. And so good idea, but it's a little bit off. It's slightly off. So this will be a different composite function. I can think of, what if we switched the two of those things, though? What if we did x plus 1 and the square root of x? Now if we take this and plug it in there, it would be that original function. So you had the right idea, and maybe you were thinking of plugging them in the other way.
Yeah.
But I had just wrote it down like this already, so. But yeah, that's good, right? Because then if we take this square root and we plug it into that function, that's what this notation means. It's exactly what the original was. I'll just write down another one, so just to show you that there's more than one. This next one is not too easy to sort of come up with, maybe. But what if we had like f of x was x squared, and then g of x was the square root of x plus 1. So like we have what we want inside the square root, and so we're going to square it to get rid of the root. That could be interesting. Although there might be some domain issues with this one, but let's ignore that for right now. If we had this situation and we plugged one into the other one, we would end up with this. And when we square the square root, it just goes away and we end up with what we wanted. And so you can see what I mean by there's infinitely many answers here, because we could just make this like a cube root, and then we've got a cube. And And we can make that a fourth root and a fourth, and a fifth root and a fifth, and we can just like keep doing that forever, right? So there's infinitely many very similar answers, at least. I was hoping to get you guys to try these. Maybe I'll start with that next time, actually. I think I might start with that next time. I think what I'm going to finish with... Are there questions about this right now? Or I'm just going to push the page up. We'll come back to this next time and finish this one off. I just wanted to show you where this stuff can be used. And your page doesn't have this. Remember, I've been trying to add in to the notes things that are applications of this stuff. And so this is my addition that I just added it. I didn't do it on your piece of paper. And you don't need to know this. You don't need to write this down necessarily. I just want to show you where we might end up with a composite function. Because remember last time how I said like, oh, I think math teachers just make up weird things sometime to trick us. And I used to think that about composite functions too. But here's a situation where we might end up with a composite function in the real world. So let's say we had some population of rabbits and it occupies a circular area. And so we know that area equals pi r squared. And over time, the population changes, right? So let's say there's a lot of food one year and the population grows. Well, the circle is going to get bigger. Their population where they live is going to get bigger. Maybe the next year, there's a lot of wolves around, and so there's a population would decrease. Right? So we've got this situation where the rabbits live in the circle that has radius r, but r changes. And what I wrote down here is maybe r is a function of time itself. And so maybe r, the radius, changes over time. And so sometimes the circle is bigger, and sometimes it's smaller. You guys kind of see that situation? And so if we wanted to write an equation of a population, write the equation that would tell us the area occupied by that population at some given time, we could write down the pi r squared equation, but r itself is a function of time, and so we would need to put this r into there, and we would end up with a composite function. And we can see, right? We can just see. It used to be this, and now it's got something else in there. We took the r out, and we plugged in what r was. And this is now a composite function. And so anytime there's an equation that you want to use, and something in the equation has its own equation, you use this. And it comes up a lot in science, or in business, for example. I used this business example earlier. Like, if you ran a business and you had an equation that had your profit, and your profit is how much stuff you sell minus how much it costs to make. Each one of those components has its own equation, right? How much it costs to make stuff has its own equation, and then how much you make via profit has its own equation. And so that is just, a very simple real-world composite function. And it happens a lot in science in general, I'd say. So we'll come back to this. We'll finish this one off next time. We've got 5 minutes, which is just enough time to do our quiz this today, and so I'm going to stop right here and use the last 10 minutes on our quiz. Are there questions about this?